Okay, so the second speaker of the morning is Benjamin Basso, who will speak about the thermodynamic limits of fishnet graphs with various boundary conditions.
Okay, well, thank you very much for the opportunity to be here and for organizing this wonderful workshop in this wonderful city. The talk will be about high energy physics, or at least the motivation is coming from. But I would like to convince you or to show you that it has a lot to do with the topic of this meeting, which is in particular integrability. And as you will see also some phenomenon that we heard about last week and this week as well, this limit shape phenomenon that we observe, or that we believe we observe also in high energy physics context. And okay, since it is some calculation with many boundary conditions involved, I had many collaborators. And so I don't know, I'm not giving you the references, but you can check and find the paper if you're interested. So okay, it's not working anymore. Yeah, it is. Ah, okay. Okay, now it's.
Also point it towards the computer. Is it connected?
Yeah, everything was working like 2 minutes ago. So the pointer is working, but okay. So it's a bit random. Well, okay, there is randomness in the. So the motivation, just a bit of high energy motivation to begin with. So the main goal is to try to understand the dynamics of planar graphs in a higher dimensional field theory and their relation to two-dimensional sigma models. So that's a very old idea that goes back to Toft, to Polyakov, and in a more recent setup, Maldacena, which is that planar graphs should have something to do with string theory, or that there should be behind any kind of planar limit, some sort of sigma model or some string theory behind. And one of the targets that one of the theories that crystallize a lot of attention is the famous maximally supersymmetric Young-Mills theory in 4 dimensions that we heard about last week in the talk of Alessandro, because this is one setup where everything is kind of crystal clear, or at least we think we know what kind of string theory dual we should be aiming at. It's some superstring theory in some curved background, which is ADS5 times S5. And on top of that, we also think that the theory is in the planar limit, so in the limit where the planar graph dominate, integrable, which means that we have exact method for summing over the planar graphs, for calculating planar graphs, and interpolating between the two regimes where the field theory is tractable and the string theory is tractable, such as to see that they are indeed the same. But everything is kind of conjectural, because these are very complicated theory with, well, complicated action and rules. And so it's hard to be rigorous, and also it's hard to actually trace back the origin of integrability, so understand where this integrability is coming from and why is this theory in particular integrable. So of course there is some reason to believe that it has a lot to do with the fact that here we are dealing with the most symmetrical, supersymmetrical theory we can think of in 4 dimensions without gravity. But okay, beyond that, it's kind of difficult to see how integrability originates in this theory. It's not totally hopeless either, and there are some progress along this line, notably by Niklas, trying to show integrability from the first principle. But most of the progress has been made by using a different type of techniques, which is to bootstrap. So bootstrapping is try to convince ourselves that a solution should exist, and we try to write down all the conditions and find a solution, or at least the minimal solution, the one that seems the most reasonable, and then we check. Okay. So the progress is difficult, although we know a lot about the solution, we think. But what is interesting is that there are also simpler examples of theory where we still have planar graphs and so on, which are the so-called fishnet theories. So these are kind of relatively old theories in a sense, because the first paper on the subject was by Zamolodchikov in the 80s, but they kind of reappear recently in the work of, sorry, it should be Gurdogan and Kazakov, and studies in connection with n equals to 4 and other supersymmetric field theory. It was realized that they form actually a huge family of planar QFTs. So in a sense, all these QFTs are sort of fabric that give us some fishnet graph, some planar graph that we may try to analyze and resum, such as to see if they can teach us anything about, for instance, sigma model or the connection to string theory. One thing that is worth noting is that these theories are not necessarily supersymmetric, so it's showing that there are also some situations where we don't have supersymmetry, but still we may have integrability, but they are still conformally invariant. So conformal symmetry seems to play an important role in underlying the integrability here as well. And the reason why we like them, this theory, is that they are kind of simpler, and that's already obvious from the point of view of the graph. If you think about drawing all the graph of n equals to 4, it's a huge mess. And graphs by themselves are not gauge invariant quantities, so it's not clear if we are looking at something meaningful. Here, the graphs are meaningful by themselves, and they are also very transparent, or suggesting some integrability structure from the regularity of their form. So they form some regular lattice structure, which is why they are called fishnet graph by Zamolodchikov many years ago. And another reason to be interested in this fishnet graph is that they are intimately related to conformal spin chain. So the usual XXX spin chains that we like, when we generalize them to representation for the Hilbert space, which are not just finite dimensional or highest weight, naturally generate fishnet graph in a way or another. So it's a way of representing, in a sense, this conformal spin chain. And as we will see, there are also some connection with sigma model, and as I mentioned, to supersymmetric theory to n equals to 4. So the hope here is to be more rigorous and perhaps prove integrability, or I don't know, develop some new techniques, and possibly draw lessons for more sophisticated theory like n equals to 4. But by rigorous, I don't mean, you know, mathematical rigor. I would say to try to be more rigorous that we are usually for an average physicist. Okay. So here is a Lagrangian of the theory. I'm writing it down once and for all, because we will focus directly to the graph, but it's just a very simple looking theory with two scalar fields, which take value in the representation of SUN. So these are just n by n matrices, which we contract trace over. And the only interaction that we allow is given by this quartic interaction, which is chosen in such a way as to produce only very peculiar graph in the limit, in the planar limit. And here I'm mentioning that it's connected to n equals to 4. I will skip that, but there is it's not immediately obvious, but there is indeed a way of getting this theory directly from n equals to 4. Super young, yes. But, sorry, the point that I wanted to emphasize here is the fact that when we start drawing the graph of this theory by following the standard rules and go to the planar limit, we find that all the graphs look more or less the same, meaning that the bulk of any graph in this theory will look like some regular lattice of this type with 4-valent interaction here. Okay. The only thing that will differ from one observable to another, depending on what you are trying to calculate, are the boundary conditions that we will impose on these lines, the external lines. Okay. We might decide to wrap them. We might decide to pinch them. We might consider also some more complicated pattern that does not look like just a rectangle, but some more fancy domain. Okay. And again, that looks like just a lattice, but what we mean here is that every line is a massless propagator in position space. Yes?
What you show here reminds me of what mathematicians call square tile surfaces. So I was wondering if you know about
square type surfaces.
Square tiled surfaces that are made. The dual would be just squares which you glue by respecting the orientation.
Okay.
So I was wondering if no.
Well, I'm not
Yeah,
aware of
you're
this,
not
but I would be happy to hear more about it. So the rule are that every point is an interaction point in position space, or in the ambient space, which is a Euclidean, a four-dimensional Euclidean space, and every line is a massless propagator. Okay, so the inverse of the square of the distance between the 2 points. Okay, so in the end, when we want to calculate this graph, we want to integrate over, make every point fluctuate and calculate it, and that's in general a very complicated Feynman diagrammatic calculations that we can do sometimes, when there are not too many loops, not too many variables to integrate, but gets horribly complicated. So also at a practical level, having integrability here means that we may hope to be able to calculate a very complicated class of Feynman integrals, which may have application to some calculation in high energy physics, like in QCD, for instance, because this kind of Feynman integrals, they appear as master integral in other theory as well. And well, the integrability of the theory here is kind of linked to this vertex and the fact that it is conformally invariant in 4 dimensions, and that is something that has been explored in the past, notably by Sasha Zamolodchikov. But the topic I'd like to discuss today is more about taking some thermodynamic limit, not trying to calculate one graph, but to think more like, at a larger scale. So what kind of thing can we say about the behavior of this graph when there are many intersection points and so on? Do we get something that looks like a smooth limit, like we are used in conventional statistical system, or do we get something crazy, or what? We definitely hope or expect to find some relation with a string worldsheet, with string being understood here in a very loose way, I would say. I don't know if it is truly a string and blah, 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 but a two-dimensional object that vibrate in some space. And in principle, since we have this relation to n equals to 4, we could think that we can just start from n equals to 4 and flow down to the fishnet theory. But it's hard to follow the string duality in this case or the way to the fishnet theory, because in the procedure, we are sending the Young-Mills coupling to 0, and if you are familiar with the correspondence, you know that it means that we are essentially dealing with a very curved ADS background. And very curved ADS background means in practice that the worldsheet is not very tractable, so it's not even clear what we should do with it. But okay, if we forget about that and we focus on what has been done by Zamolodchikov, then we notice that there is already some sort of pioneering work in the direction of trying to take the thermodynamic limit. So this is the paper of Zamolodchikov, where it's written that it's considering the infinite volume partition function for this system that I've just mentioned. And he calculated exactly the free energy. And what he found, under the assumption that there is a thermodynamic scaling, is that it is essentially controlled by what we call a critical coupling, which is this funny number. Okay. So one may think that the graph in the theory, as we tune the coupling to be close to this value, will essentially become dense. It will start behaving like some sort of smooth surface. That's the idea. And the question I would like to address today is, well, what type of effective two-dimensional effective field theory description do we get here, and how does it depend also on boundary conditions? So is this result something that we should think as being somewhat universal or not? Okay. And there will be two sets of fishnet that I will be considering, essentially the same type of boundary conditions that we've seen also in the past 2 weeks, like the periodic one. We think we would put the theory on the cylinder, or I mean, the graph on the cylinder. And some others said that will be closer in spirit to this domain wall partition, the domain wall boundary condition. So the periodic fishnets, they are naturally associated with some sort of operators that you can think of as being some transfer matrix, which is an integral operator that does the job of, adding a ring of propagator, okay, in the graph. Such that if you iterate it many times, you will get a bigger and bigger graph, all with the condition that they are periodic in one direction, okay? So this is like when, we often do that in physics when we have this Bethe-Salpeter approach, where we want to resum a particular class of graph, which we call ladder graph, which are generating by a kernel. So here the kernel is just whatever we get from the field theory, which is this propagator stretching between points and so on. And this is a quantity that is nice to consider because it's a finite operator in principle, and it has conformal symmetry, which is realized here by some differential operator. Okay. So as I said, if we want a bigger fishnet, we just iterate this this operator, and we will get whatever fishnet we want here. Okay. So M here is a number of circles, which are called wheels sometimes, and L is the length of the spin chain, if you want to think about this as a spin chain, or the number of, I think they are called spokes or whatever, rays. But we would like to, as I said, we would like to understand what happens when we take L and M to be large. So in conventional system, it's like looking, at the eigenvalue of this B operator and trying to look at what is the smallest energy, blah, blah, blah. Okay. So the eigenvalue problem consists in diagonalizing this BL and simultaneously the conformal generator that will give us some label, scaling dimension and spin, which are just the eigenvalue of the dilatation operator. Sorry, the eigenvalue of the dilatation operator and of this this operator Lorentz. So. So there will be here we will be classifying some representation of this algebra using the eigenvalue of D and the spin, the Lorentz spin.
So how does it act on the X or Y variables in your? It's really.
So here we no, this is acting on the psi. On the function psi. This is just the integral representation of the operator. The Y are integrated here. Yes.
But the X or Y represent momentum in 4D?
No, there are positions. There are positions. Yeah. It's really a position space diagram here.
Okay. And then the operators act on the position?
Well, this operator act on this. Sorry. Okay, this is on one variable. If you want to act on this function, you will actually have to take the sum of the action on each variable.
You have to act on all variables at the same time.
Yes, sorry, I was a bit fast. It's this is the action on a single field, but of course, when we take tensor product, we'll have to. Is it, well, I think it's not, no, I think you can put it out here, yes, I believe.
Okay.
I don't think it's a typo, but okay, that's that's a good question. Actually, I have a doubt now that you ask, but yeah. Okay, as you can imagine, I will be dealing with the picture and not really with the operator, but anyway. So when the length is small enough, we can essentially, the global symmetry is enough, to disentangle the representation, and then we can do some calculation, and that was done in this paper very precisely, and that's the end of the story in a sense. But for bigger length, it's like the usual story with spin chain. We need more conserved charges. We don't have enough symmetry, except if we have integrability. And a key observation that has been made and proven in this paper is that this operator B can be indeed embedded or fall inside a family of commuting conserved charges. Okay, so there is a way of constructing transfer matrices with the right symmetries and so on, and with some spectral parameter, which is such that when you evaluate it at a particular point, you reproduce precisely this operator B. Okay. The difficulty in diagonalizing this object is that you have to cope with, you have to deal with this unusual Hilbert space. By unusual, I mean that we are dealing with infinite dimensional representation of this conformal algebra, which are taken from this complementary or principal series, and that is not something that is easy to live with. In particular, as far as I know, there is no beta on that, so you should immediately go to some more sophisticated method like the separation of variables. And on top of that, you have to do it for a higher rank model right away. Okay, it's not. So it's a lot of complication. There is a kind of way around, which is to try to focus, first of all, on the spectrum of local single trace operators. So these are whatever operator will appear when we consider a generating function. So the sum over the action of this B, so the sum over L, M here, which is essentially what we will do if we calculate a correlator in the fishnet theory. We will sum and add as many wheels as we can, with a power which is g to the 2L, which is a coupling constant, which is just a parameter for the expansion of the graph. And at large distance, the state that will matter, the state that will dominate, and so on, they will be associated with solution to this equation, as has been shown in some particular example here. If you can solve these equations, then you will find essentially the scaling dimension of the local single trace operator of the theory as a function of the coupling. This is what people will do usually. They will look at some local operator, calculate the divergences, and extract the anomalous dimension. This is this calculation here, and you can, in principle, write it also implicitly in this form in this theory. That's the idea. So why is it interesting? Because we have some alternative strategy for calculating the scaling dimension. In particular, we have a TBA strategy which is inspired from n equals to 4 superior Mills. So in n equals to 4 superior Mills, people come up with this idea. And here we can just recycle it or reinterpret it. And the core idea is that we should switch to a different graph building operator, which is not related, to the evolution in the closed string channel, but in the open string channel. So instead, we consider this pizza slice here. We think about it as some evolution operator, and we think about the graph as just being, L copies, L action of this operator. So it's an operator which has a bit less symmetries, because we are fixing some points, 0 and infinity, so we just have dilatation and Lorentz that remains. But the good thing about it is that the boundary conditions are simpler. And in this case, we can solve the problem exactly, or at least people could solve the problem exactly. So the way I like to think about it, and the way people think about it in n equals to 4, is that you should think about each line here just representing the trajectory of magnon, if you want, which carries some label for the harmonics in the sphere in S3, and carries some momentum, which is just an imaginary scaling dimension for dilatation. So that's just a system that has some particle that can carry some energy and also scatter with each other, and which have these nice properties that their S matrix is totally factorized. So I think I will have to be a bit faster. So what the TBA does essentially is to calculate this grand canonical partition function of this power of the graph. Okay. So, and if you can do this calculation, what you get from the free energy is precisely the scaling dimension of the operator you're after. So now I will skip the detail of deriving the TBA equation, because I think Didi now will do it, maybe? No? No, Didi now will not do it. You can write TBA equation for this scaling dimension. So you have to introduce this y function. And after solving this equation and plugging in this free energy formula, you get the scaling dimension you're interested in. That's the idea. The points that are interesting to observe is that, first of all, the length of the chain acts as inverse temperature here. Okay, that has to do with the fact that we are iterating in this direction. And the coupling constant is just something, that keeps track of the number of magnon we are summing over. So it's just a chemical potential. So changing the coupling constant is like essentially looking at different contribution in this series. So just looking at different value of the magnon number. So they are all known, and they are all known, and they are given in terms of gamma function. But they are a bit bulky. I don't want to write them down, but everything is known here. So. Yes. Yeah. Yeah, that's because in this, yeah. What does it mean? Well, that's because you can.
I can compute thermodynamics fine.
That's essentially because when you think about the two-point function, it's like you can map it to a cylinder, with one operator at one end and another operator at the other end.
So energies are scaling dimensions.
Yes, the energy is a scaling dimension in this picture.
So
Yeah.
you have a spin chain, you have excitations.
Well, it's not quite a spin chain anymore, but okay, maybe you can call it. Okay, perhaps everything is spin chain in the end, but it's a gas. It's a gas of particle. Yeah.
So you have excitations.
Yeah.
Every excitation has energy.
Yeah.
And this is what we associated with energies.
Yes.
It's essentially a computation of energy of certain excitations.
It's a calculation of a free energy on a cylinder.
Energy is one function, is one number.
Yeah, it's a number. No, then you have to do excited state TBA. Yeah, okay. So there are indeed some more complicated version of this TBA that capture excited state, which are different operators, yes.
And that number, which is here, is the lowest number.
This is for the so-called ferromagnetic vacuum operator, which is the one which has indeed expected to have the lowest scaling dimension. But it's just a number which is a function of the length and the coupling, indeed. Well, the scale of the cylinder is just giving you, a volume factor. So the partition function, the log of the partition function is the scaling dimension times this volume, if you want. The volume you forget, the scaling dimension you calculate.
Is this a number or
It's
a
something? It depends on L.
L is the length of the cylinder?
Yes. And well, L is a number of, L is the length of the operator here. You see at the middle you have an operator which has a certain number of lines which are emanating from it, yes? The length of the chain. And G is a coupling, which you can take to be whatever you want. L and G. Two numbers, yes, yes. It's a complicated function. It's extremely complicated function, yes. Yes.
I'm sorry, one more question. Suppose somebody drew me this function, the function of operator.
Yeah.
What do I learn from it? Which part?
There are some funny, there are actually some things that are funny about the spectrum in this theory. So you can fix some L and plot the coupling, and you will see that the scaling dimension at some point develops some sort of square root behavior, which is associated to this approach of this Zamolodchikov critical coupling, for instance. So this is something you may look at. But there are very nice plot actually in a paper which, well, there is a paper by Gromov and collaborators where they have where they are plotting the solution of this TBA equation. Actually, not TBA, but another set of equation which is believed to be equivalent. And you can see this energy level, moving in the coupling as function of the coupling, if you're interested. Okay, so well, the thermodynamic limit is bringing some simplification, as you all know, because we take the temperature to go to zero, or this L to be infinite. So the lightest mode are the ones that dominate. And what we find is that we develop some sort of Fermi sea, depending on the value of the chemical potential. Okay, so the bigger the chemical potential, usually the bigger is the sea. Okay, so by changing the coupling, we change the Fermi sea, and the idea is that we will reach Zamolodchikov critical coupling when we send the Fermi gap here, the Fermi rapidity to infinity. Okay, and we will occupy all the states. Okay, that will be what we call the dense phase. What is the denser possible configuration? And here are just the equation you have to solve. There are linear integral equations with some explicitly non-kernel. You calculate, you go to the limit when b goes to infinity, and you get indeed this value that was first obtained by Zamolodchikov. So that is a confirmation that we are going to the right place. So we can do actually better than that. We can do a duality transformation. Since we're interested in the limit when everything is filled, it's kind of more natural to think about what is filled as being empty and what is empty as being filled. That's a particle Hall transformation. And that's just a sequence of steps that we have to take, like inverting the kernel, doing some massaging. And that'll give us an entirely different set of equations, which is nonetheless totally equivalent. And we can try to interpret this set of equations. And what is quite remarkable is that we essentially recover some building blocks which have been known for many years, like for instance the kernel of the 06 sigma model, which has been found by Zamolodchikov, and also some dispersion relation, which is just dispersion relation for a massless particle on a lattice. So the interpretation we could make of this dual equation is that they describe particles that scatter like in this two-dimensional 06 sigma model, but are massless, which is just not like in the 06 sigma model. And the idea is that we are not actually dealing with 06 sigma model, which is just, you know, a sigma model on the sphere, but instead with a pseudosphere. So by changing the sign of the radius of curvature, it is known that it's actually completely annihilating the gap of the theory, and that we will get instead gapless excitation. So the idea is that the dual picture is in fact what we were seeking before, which is just the continuum limit of this graph, and which is given by a sigma model. So that's a bit like the usual story with spin chain, where you find, for instance, O3 sigma model and so on, except that here it is non-compact because the symmetry group is non-compact. Okay, so we get ADS5, which is anti-de Sitter, which is a pseudosphere. So anyway, there is a way of rethinking about all of this in terms of this operator which I introduced earlier, and the idea that we are effectively in the dual picture is effectively diagonalizing this graph binding operator, and it is giving us its eigenvalue in the form of something which is controlled by Zamolodchikov, and which is just a vacuum energy density of the chain, if you want, which is a number, and an Hamiltonian, which is associated with this ADS sigma model. Okay, so that's what we get from this dual picture. So, okay, I hope I did not lose you on this, but okay, the key point here is that we reproduce Zamolodchikov, and on top of that, we learn something about how these graphs behave, you know, at large distances. I should stress that this is all good description when the sigma model is weakly coupled, which is only possible when the length is large and the energy is small. If you excite too much your fishnet, you will eventually start feeling the discretization, and you will no longer be you will no longer be dealing with a smooth picture, but you will get something which is more discrete, of course. Okay, so now I should continue with the open fishnet, if all of this was clear. And so the other calculation that we can make, and which you will see is way simpler, is instead of wrapping the line around, so we still have this sample, you know, this piece of fishnet here. Instead of trying to wrap the line around and so on, we just pinch them at some point. So because I have line at the left, right, bottom, and top, I need 4 different points. And so what I get is a 4-point function. It's a correlation function of the theory that depends on the position of the point and also on the integer, you know, the number of line n and m, which I have on my fishnet. Okay, so before it was L and M, I switched, now it's M and N, sorry about that. So different author, different letters. It's a function of 2-cross ratio because the theory is conformally invariant, as you know. We can always fix 3 points to be whatever we want. And the fourth one is in a plane with parameter z, which is just a complex coordinate in the plane. Okay. So it's a priori quite a complicated function of z bar, m, and n. But it happens to be secretly very simple. And there is a way of doing, a physicist way of finding the answer, which is a bit cheating, but gives the answer, which is based on essentially, well, mapping this graph to what is called a dual graph. That I'm pretty sure you all know that we can draw a dual lattice to this original square lattice, and the dual lattice receives this interpretation that is describing an amplitude. So you should think that you have incoming particle P with momenta P1 and P2, which are scattering with each other and eventually outgoing in P3, P4. And the relation between the momenta and the position is this one. So one is the difference of the other. And it's not really simplifying the problem, but a priori, because it's still a very complicated Feynman integral in momentum space this time. But the point is that amplitude are extremely constrained objects. They have like I mean, their analytical properties cannot be arbitrary. They have cuts, but these cuts are extremely constrained. There are these Steinman relations, which are consistency conditions on the cuts for double discontinuity, notably. And that gives a lot of information about the type of object you should have. So if you already have some insight about what you could possibly get, once you add this layer of constraint, mathematical constraint, if you want, that's often, trim down the space of possibility to a smaller options. And we did have some extra insight from integrability. I will not mention everything here, but perhaps the only thing that you should remember, if you want to remember something, is that we can calculate this graph and that they are given by the determinant of some Henkel matrix. Okay, so that is something you're probably very familiar with. You've seen that in integrable system everywhere. Here, what is cute or what is interesting is that this is actually the answer for a Feynman diagram, also for a Feynman integral. And the entries we can read from the simplest possible case where we have only one line here and arbitrarily many in the horizontal direction. And these are called the ladder function. So these are combination of polylogarithm which have been calculated many years ago by these people. Okay, so there is again, as I said, I will be fast because I think I'm. So there is a rigorous approach which is again based on this open graph building operator, the one that I mentioned briefly but did not write down. So it is written somewhere in this paper here, I believe. And the claim is that you can diagonalize it explicitly, so you can construct the exact wave function. Okay. And once you have the exact wave function here, you can write some sort, and using the completeness of the basis, you can write an integral representation for the correlator of interest, which is just iterating this guy n times. And at the very end of the process, pitching the point here to be some very special boundary condition, some very special value. So that gives an integral that you can write. If you want to see it, you can open papers, but it's explicitly known. And what is nice is that if you massage it long enough, you find actually that it can be written in this very form, which is a matrix model-like integral with some Vandermonde and some complicated potential, which encodes the information about the cross ratio here, Z and Z bar. Okay. So the determinant follow immediately. So if you are familiar with Vandermonde, you get determinant. What is nice about it is that we can also go directly to the thermodynamic limit by taking m and n to be infinity. So this is the usual large n limit. We get some potential. As you all know, we go to this, we look for the equilibrium solution. And here is the equation. Sorry. So, okay, here's the equation. You should set psi to 0. Sorry, there is a typo here. Here's the equations that you get. And this is not a new equation. It's just an equation that has been seen many times in the past. And the solution was given in particular by Niklas and collaborators some years ago. So what we can do is just take this solution and calculate the free energy of the graph and see what we get. What type of object do we get and how different it is from. So well, that we could do. So we took again, sorry for rushing a bit, but we took the integral, the log of the integral, we divide by the number of here is what we get. Metric representation of elliptic integrals. The thing that is funny, which is perhaps not that surprising, although at the beginning we found it terribly annoying, is that it depends actually on the aspect ratio of the fishnet. So we have n in one direction, m in the other direction, both are large, but we are taking the ratio to be fixed. And this is a number that go from 1 to infinity in our notation. And it's, well, it's just very annoying a priori because we were expecting to find something that is universal, like perhaps the same bulk energy, bulk free energy as we had for periodic fishnet, just a common law. And instead, what we find is something that depends on the ratio of the fishnet, which certainly goes against this universality a priori. Okay. So, yeah, sorry, I was fast. E and K are complete elliptic integral of first and second kind. And Q is related to this K this aspect ratio by this parametric. You have to solve Q as a function of K and plug in. Yeah, it's all parametric. We could not do better than that. Okay. Well, the solutions that we took from Niklas were also parametric, so we stay parametric. We can nonetheless get rid of the parametric representation numerically, and we can verify that this is the right answer. It's effectively interpolating nicely the result from the determinant. So there is no doubt that this is a curve. Okay, just so happen to depend on this aspect ratio. But now, no matter how we look at it, numerically, and we did some continuation elsewhere to see, we could never find anything that get close to this value of Zamolodchikov. So the value of Zamolodchikov is somewhere here below, I forgot where, and we could not reach it. So it's just two different free energy. So there is a loss of universality. So that was a bit of a puzzle for us at the beginning, because we believed strongly in the universality of the thermodynamic limit, which would say that, okay, possibly for some systems which are local enough and with regular enough boundary condition, we should get always the same bulk energy, free energy. Yes, I guess we would agree on that probably. But of course, then we've learned about what you guys knew for a very long time, which is that it happens that sometimes the free energy are different. And it happens, there are phenomena where, especially with the lattice model, which exhibit some strong sensitivity to the boundary condition. And we've heard about it like last week and this week, notably the 6-vertex model, which we show very different thermodynamic behavior depending on whether we use periodic boundary condition or domain wall boundary condition. And the interpretation, you all know, there are two different phases, one that is melted, the other one is frozen. And the analogy with what we have is mathematically convincing, at least, because the periodic boundary condition gives rise to a TBA, solution to a TBA equation, and the domain wall boundary condition gives rise to a determinant, which is also what we have. So we have two different types of mathematical object a priori. Also, physically, we want to possibly argue that this has to be expected because in our case, the corner of the picture are actually operators that carry a very large dimension. So from the worldsheet point of view, from a low energy effective field theory point of view, it means that we have an extremely excited state at the boundary. So, and that is perhaps not that crazy to observe that this very excited state is kind of stretching the worldsheet very far away from the equilibrium, and this over a relatively large distance. So, of course, this is whole speculation because we don't have nice picture like people have with these Aztec diamonds and so on. We don't know how to plot something that will effectively look like that. But at least what we observe is possibly, how to say, encouraging and going along these lines that such a phenomenon is present here. So. What is unclear to us and what we've been fighting with without finding any solution is whether we can still hope to have some sort of continuum description, some sort of sigma model description of what is happening here across the entire graph. So that's something we could not elucidate. So anyway, there are also other limits. So I will skip, but it's just showing that indeed we can get very different things. And I will get to the conclusion. So, so I wanted to show you that planar graphs, they form a very nice arena for connecting this conformal spin chain, sigma model, and so on. And they also have something to do with lattice integrable model. At least we find some systems which are very close to the one that have been studied in the past, although with some non-compact symmetric group. But we observe similar phenomenon like this strong sensitivity on the boundary condition and so on. It's not entirely clear what it means to us, at least, what it is there. We don't know how universality is, for instance, and we don't know what will be the general behavior for a general graph. So here we just look at two family of graphs, say, two type of boundary condition, but we could imagine more complicated graph. And the question is, okay, what should we expect in this case? And can we have some sort of effective field theory understanding or description of what is happening? That is something that I would at least personally like to know, because I I would like to have some sort of ADS description of all of that, if it is possible, and understand it from this side. Thank you.
All right, thank you very much. Any questions? The other questions?
Yes, thank you. At 2 points, at least in the talk, you showed us this BL operator, which acts on wave functions. And you, if I understand correctly, in at least several situations, you are able to diagonalize this operator. So I was wondering in which space this wave function, these eigenvectors, are there polynomials in the variables or rational functions? Or what is the...
Okay, that's a good question. So in the general case, in the case of the closed, for the closed case, I don't know. So what I showed you is possibly one way of getting the eigenvalue without actually addressing the problem from the very beginning, because I use this TBA, yes, to bypass the difficulties. So that's in the case of the open chain. Then it's known what it is. So I just can't recall, but this is a tensor. So the Hilbert space it's a tensor product of complementary representation in the complementary series of the conformal group. So okay, this is the Hilbert space. Then in this space you can have several bases possibly, which I don't know. I don't know how to answer it. Some space, infinite dimensional space.
Okay.
So.
Thank you.
Yeah, sorry. So I'm working in a bit different field, so please allow me to ask some kind of heretic questions. You started with a question from outside view. So you started with Lagrangian of a quantum field theory, two fields, matrix valued, and so on. And my question is, what do you learn from your results about, say, this quantum field theory? I would like to learn something about, say, partition functions, correlation functions. So where does this enter?
So okay, so the partition function of the field theory itself, it's not what I'm talking about. So for instance, something that we learn here from this calculation is just one correlation function of the theory. So the theory has infinitely many correlation functions. Among them, there is one that is this one with this particular boundary condition or particular operators. And that one we could calculate. So there are many more. And in general, it's hard to calculate, but there are also strategies for building a higher correlation function out of smaller one. So integrability helps developing new strategy for calculating these higher loop integrals, which would otherwise be just impossible to calculate. For the closed string observables that we talked about, so the closed spin chains, this is more directly related to the calculation of the spectrum of the theory. So the theory is local, there are local operators. Operators carry scaling dimensions. There is a spectrum of scaling dimensions that depend on the coupling constant of the theory. And one of the goals in conformal field theory, or at least step one in conformal field theory, is to find the spectrum and the entire, the set of scaling dimension. So the TBA equation and so on, they give you the answer in one way. I mean, in one form, sorry.
Is that giving you the whole spectrum, or
Okay, so that's a good point. So I was only giving here what will be the ground state TBA, like the simplest operator. There are also excited state version of it that give you access. But the completeness, I'm not sure. I think if you want to get something complete, you have to switch to TQ relation. I mean, you have to use some spectral curve, because it's easy to misstate with the TBA. It's I don't know if it's possible to write a complete TBA for the entire spectrum of this theory. I don't know.
Yeah, I had something maybe related to his question, but could you show the slide again where you had your TBA equations with the y functions?
Okay.
At some point you had that. Yeah, probably that, yes. So something very naive, but I mean, I have worked a lot on TBA, but more the Samologikov style kind of integral QFT. So I know it's a bit different, but one thing I'm always curious about is how you actually solve those equations, because I guess you have infinitely many B's, right? You have infinitely many particles, in a sense. So what do? You truncate and then solve numerically, or how do you deal with that?
Okay, so for this state, for the ground state, I think you could indeed truncate and solve numerically up to some value of the coupling.
Okay.
That's something you could do. The point is that nowadays people don't use TBA anymore. So they have this spectral curve, and usually when they want to solve something, they go immediately to the spectral curve. So, but okay, the TBA is still a way of presenting the answer, but as soon as you get it, you try to get rid of it. That's the idea.
Okay. All right, and yeah, I mean, but if you truncate, how do you know what to truncate? I mean.
Okay, that's a good point. So some of these Y are more and more suppressed because the higher the B is, the smaller is the Y, at least for a certain range of the value of the coupling. Okay. That's related to the fact that you have this fugacity and the fact that, if you are too heavy, you get suppressed at some point.
Okay.
That's the idea. But there are also some auxiliary Y, which are like, like controlling the symmetry. They are a little bit more annoying because typically they are further one. So this one you probably have to solve first, and then iterate.
For the others, yeah. Okay, thanks. I was also curious about what operator that dimension corresponds to that you computed down there.
The operator?
Delta. So you have a scaling dimension you get from this TBA.
Yeah.
So what is it the dimension of?
Okay, it's a dimension of a local single trace operator, which is the trace scalar field to the power L.
Okay.
So that's the simplest possible operator you can think of. And what is nice about it in particular is that it renormalizes with himself, with itself. So it's just, it's the same, it takes the same form at any coupling. It's just this operator. There is no mixing with.
Okay, that's interesting. So this dimension, is it related in any way to the standard scaling function of TBA? Is that
the standard?
Like the C function? So you have an integral there that looks a little bit like
no, the central charge, you mean?
Yeah. It's nothing to do.
Well, you see, it's a very non-relativistic TBA. So what do you want to call central charge here?
No, I don't necessarily want it. Is that in the formula for the delta, there is this integral there that looks a little bit like energy density in some way, but maybe I'm wrong.
Okay, well, we just have this, we have this mapping to, well, we think about the length as the temperature, this, this kind of Samologikov trick.
Yeah.
And,
okay.
Yeah, okay, I don't know how to answer, sorry.
But thanks, that clarify a lot of things. Thank you.
Welcome.
All right, okay, thank you. So in view of the time, I suggest further questions can be asked to Benjamin in the break. Let's thank the speaker again.